The universe we observe today is vast beyond ordinary comprehension, yet what we see is only a small fraction of what may actually exist. Every direction we look, space stretches outward, filled with galaxies, stars, and cosmic structures that hint at an even larger reality beyond our reach. However, there is a fundamental boundary to human observation, a limit not defined by physical walls, but by the speed of light and the age of the universe itself. This boundary is known as the observable universe, and it represents everything from which light has had enough time to reach us since the beginning of cosmic expansion. Light travels at a finite speed, and although it is incredibly fast on human scales, the universe is so large and so old that even light has only had a limited amount of time to cross it. This means that when we look into space, we are not seeing the universe as it is right now, but rather as it was in the past. The farther away an object is, the older the light we see from it. In the most distant visible galaxies, we are observing light that has traveled for billions of years before reaching our telescopes. In a sense, looking into space is also looking back in time. This creates a natural limit to observation. There are regions of space so far away that their light has not yet had time to reach us. Even if those regions contain galaxies, stars, or even entire cosmic structures, they remain invisible to us. Beyond a certain distance, the universe becomes completely unknown, not because it does not exist, but because its light has not yet arrived. This hidden region beyond the observable boundary may contain structures similar to what we see locally, or it may contain entirely different forms of cosmic organization that we can never directly observe. The observable universe is estimated to extend about 93 billion light-years in diameter. This number can be confusing because the universe is approximately 13.8 billion years old. The reason the observable universe is larger than the age of the universe multiplied by the speed of light is due to the expansion of space itself. As light travels toward us, space is also stretching, increasing the distance it must cover. This means that the actual current distance to the most distant observable objects is far greater than the time their light has been traveling suggests. Within this observable region, we see an extraordinary level of structure. Galaxies are not randomly scattered, but are organized into clusters, filaments, and vast cosmic webs. These structures are shaped by gravity acting on both visible matter and invisible dark matter. Over billions of years, gravity pulls matter together into dense regions while leaving other areas almost empty, creating a universe that is both beautifully structured and deeply uneven. Yet, even this structured universe is only a partial view. The regions beyond the observable horizon may contain similar structures, or they may differ in ways we cannot predict. Because we are limited by the speed of light, there is no way to directly confirm what exists beyond this boundary. This creates one of the most profound limitations in cosmology. We are confined to observing only a finite bubble of the universe, while the total extent of reality may be vastly larger or even infinite. Another key limitation of human vision comes from the early universe itself. There is a point in cosmic history beyond which light cannot reach us at all. This is known as the cosmic microwave background radiation, the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely for the first time. Before this moment, the universe was filled with a dense plasma that trapped light, making it impossible for photons to travel freely. This means that the earliest epochs of the universe are completely hidden from direct observation using light. We cannot see the moment of the Big Bang itself, nor the earliest fractions of a second after it occurred. Instead, we rely on indirect evidence and theoretical models to understand what might have happened during those earliest moments. This introduces another layer of uncertainty into our understanding of the cosmos. Modern telescopes, both ground-based and space-based, have extended our vision farther than ever before. Instruments such as the Hubble Space Telescope and the James Webb Space Telescope allow us to observe galaxies that formed very early in the universe's history. These observations show us galaxies as they were billions of years ago, giving us a glimpse into cosmic evolution. However, even these powerful tools cannot break the fundamental limits set by the speed of light and cosmic expansion. There are also regions of space that are permanently beyond our reach due to the accelerating expansion of the universe. Because space itself is expanding faster over time, there are galaxies whose light will never reach us, no matter how long we wait. These regions are effectively cut off from our observable universe. Even though they exist, they are causally disconnected from us. This means that part of the universe is not just currently invisible, but permanently unobservable. This leads to a deeper philosophical and scientific question. If parts of the universe can never be observed, how can we know they exist at all? The answer lies in the assumption that the laws of physics are consistent across space. By studying the regions we can see, we infer that similar laws likely apply beyond our observational horizon. However, this remains an assumption, not a direct observation. Another major limitation in understanding the cosmos comes from the nature of information itself. Information about distant objects is carried by light and other forms of radiation. However, as light travels across vast cosmic distances, it becomes increasingly redshifted and weakened by expansion. This makes extremely distant objects harder to detect and study. Eventually, their signals become so faint that they merge into background noise. In addition to observational limits, there are also theoretical limits to our understanding. Some aspects of the universe may be fundamentally unpredictable or inaccessible due to quantum uncertainty. At very small scales, the behavior of particles is governed by probabilities rather than deterministic outcomes. This means that even with perfect instruments, there are limits to what can be known with absolute certainty. The combination of observational limits and theoretical uncertainty creates a universe that is only partially accessible to human understanding. We can build models, test predictions, and refine our theories, but there will always be boundaries beyond which direct knowledge is impossible. These boundaries define the edge of scientific exploration. Despite these limitations, humanity has made extraordinary progress in mapping the universe. We have discovered billions of galaxies, measured the expansion of space, detected gravitational waves from black hole mergers, and observed the faint afterglow of the Big Bang itself. Each discovery pushes the boundary of the known further outward, but the ultimate limit remains. One of the most fascinating aspects of the observable universe is that it is not static. As time passes, the observable region changes. Light from more distant objects continues to reach us, revealing new parts of the universe. At the same time, cosmic expansion causes some regions to move beyond our reach. This dynamic balance means that the observable universe is constantly evolving. In the far future, the situation will be very different from today. Due to accelerating expansion, distant galaxies will eventually disappear from view entirely. Future observers in our galaxy may only see a small, isolated region of the universe with no visible evidence of the vast cosmic structures we see today. This highlights how observation is not only limited in space, but also in time. The limits of human vision are therefore both physical and temporal. We are constrained by the speed of light, the expansion of the universe, and the finite age of cosmic history. These constraints define what we can and cannot know about the cosmos. Yet within these limits, the universe reveals an astonishing level of detail. From the smallest particles to the largest cosmic structures, everything we observe is part of a vast interconnected system governed by physical laws. Even though we cannot see everything, what we can see is enough to reconstruct a remarkable picture of cosmic evolution. This chapter highlights a fundamental truth about our place in the universe. We are observers located within a small region of a vast and possibly infinite cosmos. Our knowledge is shaped by the signals that reach us, and our understanding is always limited by the boundaries of observation. Yet within those boundaries, we continue to explore, discover, and expand the frontiers of human knowledge. The limits of human vision are not simply restrictions, they are also invitations to curiosity. They remind us that there is always more to learn, more to explore, and more to imagine beyond what we can currently see. Among all the mysteries that shape our understanding of the universe, few are as strange and elusive as dark matter. It does not emit light, it does not absorb light, and it does not reflect light in any detectable way. In fact, it does not interact with electromagnetic radiation at all. Yet, despite being completely invisible, its presence is written across the structure of the cosmos. It is one of the most important components of the universe, and at the same time, one of the least understood. The first hints that something invisible was influencing the universe came from observations of galaxies. When astronomers studied how galaxies rotate, they noticed something unexpected. The outer regions of galaxies were moving much faster than they should have been if only visible matter was present. According to the laws of gravity, stars farther from the center of a galaxy should orbit more slowly because they experience less gravitational pull from the concentrated mass in the core. However, observations showed that stars in the outer regions were moving at nearly the same speed as those closer in. This discrepancy suggested that there must be additional mass that could not be seen. If only the visible stars, gas and dust were present, galaxies would not remain stable under such rapid rotation. They would gradually fly apart. The fact that they remain intact implies that there is an unseen source of gravity holding them together. This invisible mass was given the name dark matter. Over time, evidence for dark matter accumulated from many different sources. Not only galaxy rotation curves, but also the behavior of galaxy clusters, gravitational lensing, and the large-scale structure of the universe all pointed toward the same conclusion. There must be far more matter in the universe than what we can directly observe. One of the most powerful pieces of evidence comes from gravitational lensing. According to general relativity, massive objects bend the fabric of space-time, causing light to curve as it passes near them. When astronomers observe distant galaxies, they sometimes see their light distorted into arcs or rings. By analyzing these distortions, scientists can map the distribution of mass in the universe. What they find is that there is significantly more mass present than can be accounted for by visible matter alone. This invisible mass forms a kind of cosmic scaffolding. It does not clump together in the same way that normal matter does, because it does not interact through electromagnetic forces. Instead, it interacts only through gravity. This means that dark matter can pass through itself and ordinary matter without friction or resistance. It behaves in a very different way from anything we are familiar with in everyday life. In the early universe, dark matter played a crucial role in the formation of structure. After the Big Bang, the universe was nearly uniform, with tiny fluctuations in density. Over time, gravity amplified these fluctuations. Dark matter, being unaffected by radiation pressure, began to collapse into dense regions first. These regions acted as gravitational wells, pulling in ordinary matter. This process eventually led to the formation of galaxies and large-scale cosmic structures. Without dark matter, the universe would look very different today. The formation of galaxies would have been much slower and less efficient. In fact, many of the structures we observe might not have formed at all. Dark matter provided the gravitational framework that allowed ordinary matter to accumulate and form stars, galaxies, and clusters. Despite its importance, we still do not know what dark matter is made of. It does not appear to be composed of the same particles that make up atoms, such as protons, neutrons, and electrons. Instead, it must consist of some new type of particle that has not yet been directly detected. Scientists have proposed many candidates, including weakly interacting massive particles, axions, and sterile neutrinos, but none have been confirmed. One of the greatest challenges in studying dark matter is that it does not interact with light. This means that traditional telescopes, which rely on detecting electromagnetic radiation, cannot observe it directly. Instead, scientists must infer its existence through its gravitational effects. This makes dark matter one of the most indirect discoveries in modern science. Laboratories around the world are attempting to detect dark matter particles through highly sensitive experiments. These experiments are designed to observe rare interactions between dark matter and ordinary matter. For example, detectors are placed deep underground to shield them from cosmic radiation, in the hope of capturing the faint signal of a dark matter particle passing through. So far, no definitive detection has been made. This absence of direct evidence has only deepened the mystery. It raises the possibility that dark matter may be even more exotic than current theories suggest, or that our understanding of gravity itself may need to be modified on cosmic scales. Some alternative theories propose that what we attribute to dark matter could instead be a sign that our understanding of gravity is incomplete. Modified gravity theories attempt to explain the observed effects without invoking unknown particles. However, these theories struggle to account for all observed phenomena simultaneously, especially in galaxy clusters and the cosmic microwave background. The distribution of dark matter in the universe is not uniform. It forms large-scale structures that mirror the cosmic web. Filaments of dark matter connect clusters of galaxies, creating a vast network that shapes the visible universe. Galaxies form within these dark matter halos, which act as gravitational anchors holding them together. In galaxy clusters, dark matter is especially abundant. These clusters contain hundreds or even thousands of galaxies bound together by gravity. However, the visible matter in these clusters accounts for only a small fraction of the total mass. The rest is dark matter, forming a massive invisible structure that dominates the gravitational landscape. The presence of dark matter also affects the evolution of individual galaxies. It influences their rotation, structure, and stability. Without dark matter, galaxies would not rotate in the way they do today. The outer regions would not have enough gravitational pull to remain bound, leading to instability and eventual dispersion. On the largest scales, dark matter is essential for explaining the uniformity and structure of the universe. The patterns seen in the cosmic microwave background radiation, the afterglow of the Big Bang, show tiny fluctuations that match predictions involving dark matter. These fluctuations are the seeds from which all cosmic structures grew. Despite decades of research, the true nature of dark matter remains one of the biggest unsolved problems in physics. It makes up approximately 85% of the matter in the universe, yet we do not know what it is. This means that most of the universe is composed of something we cannot see, cannot touch, and do not yet understand. The mystery of dark matter is not just about missing mass. It is about the fundamental structure of reality. If we do not understand what most of the universe is made of, then our picture of the cosmos is incomplete. Every galaxy, every cluster, and every large-scale structure is shaped by something invisible. This leads to a profound realization. The universe we observe is only a partial representation of a deeper underlying reality. The visible matter that forms stars, planets, and life is only a small fraction of the total cosmic content. The rest remains hidden, influencing everything through gravity alone. Understanding dark matter is one of the central goals of modern cosmology and particle physics. It represents a bridge between the largest scales of the universe and the smallest scales of fundamental particles. Solving this mystery could reveal new physics beyond our current theories and fundamentally change our understanding of the universe. Until then, dark matter remains one of the greatest cosmic mysteries. It is the invisible framework that holds galaxies together, the unseen mass that shapes the cosmic web, and the silent partner in the evolution of the universe. It is everywhere, yet completely hidden from direct view. This chapter reveals a universe that is not what it seems. Beneath the visible stars and galaxies lies an invisible structure that governs their behavior. Dark matter is the hidden architecture of the cosmos, and until we understand it, we are only seeing part of the story of the universe. If dark matter is the invisible structure holding galaxies together, then dark energy is the invisible force pushing the entire universe apart. It is one of the most profound and puzzling discoveries in modern cosmology, not because it was directly observed, but because of what it does to the universe on the largest scales. While dark matter pulls things together through gravity, dark energy appears to do the opposite, driving space itself to expand at an accelerating rate. The story of dark energy begins with the observation of distant supernovae. In the late 1990s, astronomers studying Type Ia supernovae, which are powerful stellar explosions with consistent brightness, noticed something unexpected. These supernovae were dimmer than predicted. This meant they were farther away than expected, which in turn implied that the expansion of the universe was not slowing down due to gravity, as once thought, but actually speeding up. This discovery was shocking. For most of the 20th century, cosmologists assumed that the expansion of the universe, which began with the Big Bang, would gradually slow down as gravity pulled matter together. Depending on the total amount of matter in the universe, it might slow forever or eventually reverse into a collapse. But instead of deceleration, observations revealed acceleration. To explain this acceleration, scientists introduced the concept of dark energy. Unlike ordinary energy or matter, dark energy does not clump together in space. It appears to be evenly distributed throughout the universe, and its effect becomes more significant as space expands. The more the universe grows, the stronger the influence of dark energy becomes. One way to understand dark energy is to think of space itself as having an intrinsic property. Even empty space is not truly empty. According to quantum physics, it is filled with fluctuations and energy fields that constantly appear and disappear. Dark energy may be related to this vacuum energy, representing a fundamental property of space-time itself rather than a substance or particle. Another possibility is that dark energy is connected to a cosmological constant, a term first introduced by Albert Einstein. In his equations of general relativity, Einstein included a constant to allow for a static universe, one that neither expands nor contracts. Later, when the expansion of the universe was discovered, he reportedly called this his greatest mistake. However, the cosmological constant re-emerged decades later as a possible explanation for the observed acceleration of cosmic expansion. If dark energy is truly a cosmological constant, then it means that empty space has a built-in energy density that does not change over time. As the universe expands, the total amount of dark energy increases because there is more space, not because the energy density itself changes. This leads to a situation where expansion accelerates more strongly as time goes on. The effects of dark energy are only noticeable on the largest scales. Within galaxies, gravity is strong enough to hold stars together. Within solar systems, gravity dominates planetary motion. Even within galaxy clusters, gravitational attraction is sufficient to keep structures bound. But beyond these scales, dark energy begins to dominate. stretching space between galaxy clusters and driving them apart. This means that the universe is not only expanding, but the rate of expansion is increasing over time. Distant galaxies are moving away from each other faster and faster. Eventually, many galaxies will become so far apart that their light will never reach each other again. This leads to a future where the observable universe becomes increasingly isolated. One of the most important consequences of dark energy is the concept of the cosmic horizon. Because expansion is accelerating, there is a limit beyond which objects recede faster than light can travel toward us due to the expansion of space. This does not violate the speed of light limit in relativity because it is space itself that is expanding, not objects moving through space. However, the result is the same. Beyond a certain distance, information can never reach us. As time passes, this horizon shrinks in terms of accessible information. Galaxies that are currently visible will eventually cross this boundary and disappear from view. Future observers in our galaxy will see fewer and fewer distant galaxies until only their local group remains visible. The rest of the universe will fade into darkness, not because it no longer exists, but because it is no longer observable. Dark energy also has profound implications for the long-term fate of the universe. If the acceleration continues indefinitely, the universe will expand forever. Structures that are not gravitationally bound will drift apart until they are completely isolated. Over extremely long timescales, even local structures may become affected by this expansion. In such a scenario, galaxies within local groups may eventually merge into single large systems. For example, the Milky Way and Andromeda galaxies are expected to collide and merge in the distant future. After this merger, the resulting galaxy will become a stable island of stars surrounded by an expanding void. Beyond this region, no new galaxies will be observable. As expansion continues, the density of matter in the universe decreases. This has a direct effect on the formation of new structures. Star formation requires dense clouds of gas to collapse under gravity. But as gas becomes more diffuse and spread out, the likelihood of new star formation decreases. This contributes to the gradual decline in cosmic activity. Dark energy does not directly destroy matter or stars. Instead, it changes the large-scale geometry of space. It increases the distance between structures over time, making it more difficult for gravity to bring matter together on large scales. Gravity remains strong on local scales, but it loses its influence over cosmic distances. The nature of dark energy is still unknown. It could be a property of space itself, a dynamic field that changes over time, or something even more fundamental that we do not yet understand. Some theories suggest that dark energy might evolve, meaning its strength could change in the future. If this is true, then the fate of the universe could be very different depending on its behavior. If dark energy remains constant, the universe will continue expanding forever, becoming colder, darker, and more isolated. If it increases over time, it could lead to a scenario known as the Big Rip, where expansion becomes so strong that even atoms are eventually torn apart. If it decreases or changes sign, it could lead to a collapse of the universe in the distant future. However, current observations suggest that dark energy is consistent with a constant value. One of the most intriguing aspects of dark energy is that it makes up most of the energy content of the universe. While dark matter accounts for about 85% of matter, dark energy accounts for about 70% of the total energy density of the universe. Ordinary matter, everything we can see, touch, and detect directly, makes up only a small fraction of the total cosmic content. This means that the majority of the universe is made up of two invisible components. Dark matter shapes structure through gravity, while dark energy drives expansion. Together, they define the large-scale behavior of the cosmos, yet neither is fully understood. The interaction between dark matter and dark energy is indirect but crucial. Dark matter pulls structures together, forming galaxies and clusters, while dark energy pushes the universe apart, stretching space between those structures. This balance determines the evolution of the universe over billions of years. In the early universe, dark energy had little effect because matter was much more densely packed. Gravity dominated and structures formed rapidly. But as the universe expanded and matter became more spread out, dark energy began to dominate. This shift marks a turning point in cosmic history, where expansion-acceleration begins to shape the future evolution of everything. On the largest scales, dark energy determines the ultimate fate of cosmic structure. It ensures that the universe will not recollapse under gravity, at least under current understanding. Instead, it drives a continued expansion that gradually isolates all structures from each other. Even though dark energy is invisible, its effects are measurable and consistent across many observations. From supernovae to cosmic microwave background measurements and large-scale galaxy surveys, all data points toward an accelerating universe. This consistency makes dark energy one of the most important discoveries in modern cosmology. Yet despite its importance, we still do not know what dark energy actually is. It remains one of the deepest mysteries in physics. Understanding it could reveal new aspects of space-time, new fields in physics, or even entirely new laws governing the universe. This chapter highlights a paradox at the heart of cosmology. The universe is dominated by something we cannot see, cannot directly measure, and do not fully understand. Yet its effects are responsible for shaping the entire future of cosmic evolution. Dark energy is the force that determines whether the universe expands forever, tears itself apart, or transforms in ways we have not yet imagined. It is the hidden driver of cosmic destiny, silently shaping the fate of everything that exists. Black holes represent some of the most extreme and mysterious objects in the universe. They are regions where gravity becomes so strong that nothing, not even light, can escape once it crosses a certain boundary. This boundary is known as the event horizon, and it marks the point of no return. Beyond this surface, the known laws of physics begin to behave in ways that challenge our understanding of space, time, and reality itself. The concept of a black hole arises naturally from Einstein's theory of general relativity. According to this theory, gravity is not simply a force acting at a distance, but a curvature of space-time caused by mass and energy. The more massive and compact an object becomes, the more it curves space-time around it. If enough mass is compressed into a small enough region, space-time becomes so curved that it forms a closed boundary from which nothing can escape. Black holes are formed in several ways, but the most common process begins with the death of massive stars. When a star much larger than the Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The outward pressure created by fusion decreases, while gravity continues to pull inward. In a matter of moments, the core collapses, and if the remaining mass is sufficient, it forms a black hole. This collapse is one of the most violent events in the universe. The outer layers of the star are often ejected in a supernova explosion, releasing enormous amounts of energy and scattering heavy elements into space. The core, however, continues to collapse until it reaches a state where gravity dominates all other forces. At this point, a black hole is born. Once formed, a black hole is defined by only a few properties: its mass, its spin, and its electric charge. Everything else about the matter that formed it is lost behind the event horizon. This leads to a fascinating idea often summarized as black holes have no hair, meaning they are remarkably simple objects despite being formed from extremely complex processes. At the center of a black hole lies a region called the singularity, where density becomes infinitely large according to classical physics. However, this concept signals a breakdown in our current understanding of physics. Most scientists believe that a complete theory of quantum gravity would replace the idea of a singularity with something more physically meaningful, but such a theory has not yet been fully developed. One of the most important features of a black hole is its event horizon. This is not a physical surface, but rather a boundary in space-time. Once an object crosses this boundary, it cannot return. Even light, which travels at the fastest possible speed in the universe, cannot escape. This gives black holes their defining characteristic: absolute invisibility from the inside. Despite this, black holes can be detected indirectly. When matter falls toward a black hole, it often forms a rotating disk called an accretion disk. As material in this disk spirals inward, it heats up due to friction and gravitational forces, emitting intense radiation across the electromagnetic spectrum. This radiation can be detected by telescopes, allowing scientists to infer the presence of a black hole. Black holes also influence their surroundings through gravity. They can bend the paths of nearby stars, distort light from distant objects, and even affect the motion of entire star systems. In some cases, astronomers can observe stars orbiting an invisible object, providing strong evidence for a black hole's existence. There are different types of black holes depending on their mass. Stellar black holes form from collapsing stars and typically have masses a few times greater than the Sunday. Supermassive black holes, found at the centers of galaxies, can have masses millions or even billions of times greater than the Sunday. There is also a theoretical class known as intermediate black holes, which fall between these two categories, though their origins are still not fully understood. Supermassive black holes are among the most fascinating objects in the universe. Almost every large galaxy appears to contain one at its center. These giants influence the formation and evolution of galaxies themselves. Their gravitational pull affects the motion of stars and gas in the surrounding region, and in some cases they power extremely energetic phenomena known as active galactic nuclei. When large amounts of matter fall into a supermassive black hole, the accretion process can release enormous amounts of energy. This energy can outshine the entire galaxy in which the black hole resides. These active phases are some of the most luminous events in the universe and can be observed across vast distances. Despite their power, black holes are not eternal. According to quantum theory, they slowly emit a form of radiation known as Hawking radiation. This phenomenon arises from quantum effects near the event horizon, where particle pairs can form and one of the particles escapes while the other falls into the black hole. Over time, this leads to a gradual loss of mass. The process of Hawking radiation is extremely slow for large black holes. A black hole with the mass of a star would take far longer than the current age of the universe to evaporate completely. However, over incredibly long timescales, all black holes are expected to eventually disappear through this process. As a black hole loses mass, it becomes smaller and hotter, causing it to emit more radiation. This creates a feedback loop where the evaporation process accelerates. In the final stages, the black hole emits a burst of high-energy particles before vanishing entirely. This final event represents one of the most extreme transformations in physics. Black holes also play a crucial role in the evolution of the universe. They act as endpoints for massive stars, contribute to the distribution of energy and matter, and influence the structure of galaxies. In many ways, they are both destroyers and regulators of cosmic order. On large scales, black holes can merge with one another, producing even more massive black holes. These mergers release gravitational waves, ripples in space-time that carry information about the collision. The detection of gravitational waves has opened a new window into the study of black holes and confirmed many predictions of general relativity. As time progresses into the far future, black holes become increasingly isolated. With no new stars forming and most matter already consumed or dispersed, black holes remain as the last significant objects in the universe. They drift through space, slowly growing through rare interactions and mergers. Eventually, even these interactions become rare. The expansion of the universe separates black holes from each other, limiting their ability to interact. Each black hole becomes an isolated system, slowly evolving only through Hawking radiation. In this distant future, black holes dominate the universe both in mass and in significance. They represent the final stage of gravitational collapse and the last major reservoirs of energy in an otherwise fading cosmos. When they eventually evaporate, they mark the end of all large-scale structures formed by gravity. Black holes are also central to some of the deepest mysteries in physics. One of the most important is the information paradox. According to quantum mechanics, information about physical systems cannot be destroyed. However, if something falls into a black hole and the black hole eventually evaporates, it is unclear what happens to the information about that object. This paradox has led to many theories, including the possibility that information is somehow encoded in Hawking radiation or stored on the event horizon. Some ideas suggest that the nature of space-time itself must be reinterpreted to resolve this contradiction. Despite decades of research, the full answer remains unknown. Black holes also challenge our understanding of space and time. Near the event horizon, time behaves differently depending on the observer. To an outside observer, an object falling into a black hole appears to slow down and never quite cross the event horizon. To the falling object itself, however, crossing the horizon happens in finite time. This difference in perception highlights the strange nature of space-time under extreme gravity. In addition, black holes may hold clues to a deeper theory of quantum gravity, which would unify general relativity and quantum mechanics. Such a theory would be needed to fully understand what happens at the singularity and during black hole evaporation. This chapter reveals black holes as both endpoints and gateways in cosmic evolution. They are the final stage of stellar life, the engines of extreme physics, and the key to many unresolved questions in modern science. They bend space-time, consume matter, emit radiation, and slowly evaporate, all while challenging our understanding of reality itself. Black holes are not just cosmic objects. They are laboratories of extreme physics, where the known laws of nature are pushed to their limits. Understanding them may ultimately reveal some of the deepest truths about the universe and the nature of existence itself. Among all the questions that define modern cosmology, few are as fundamental or as deeply unsettling as the question of how the universe began. The origin of the universe is not just a scientific problem, but a boundary where physics, philosophy, and imagination meet. Everything we observe today, galaxies, stars, planets, and even the very atoms that make up our bodies, all trace their history back to a single early state of extreme density and energy. Yet what exactly that initial state was, and what might have preceded it, remains one of the greatest mysteries in science. The prevailing scientific model for the origin of the universe is known as the Big Bang theory. According to this model, the universe began approximately 13.8 billion years ago from an extremely hot, dense state and has been expanding and cooling ever since. This expansion is not an explosion in space, but an expansion of space itself. Every region of space is stretching, causing galaxies to move away from each other over time. In the earliest moments after the Big Bang, the universe was unimaginably small, hot, and dense. Temperatures were so high that no atoms could exist. Instead, the universe was filled with a primordial soup of particles, energy, and radiation. Matter and energy were constantly being created and destroyed in high-energy interactions. In this state, the fundamental forces of nature may have behaved very differently from how they do today. As the universe expanded, it cooled. This cooling allowed fundamental particles to form and combine. First, quarks combined to form protons and neutrons. Later, these particles joined to form the first atomic nuclei in a process known as nucleosynthesis. Still later, electrons became bound to nuclei, forming the first atoms. This moment allowed light to travel freely for the first time, producing the cosmic microwave background radiation that we can still observe today. This early radiation provides one of the strongest pieces of evidence for the Big Bang theory. It is a faint, nearly uniform glow that fills the entire universe, representing the afterglow of the early hot state. By studying small fluctuations in this radiation, scientists can learn about the conditions of the early universe and how structure eventually formed. However, while the Big Bang model describes the evolution of the universe from very early times onward, it does not fully explain the origin of the initial state itself. It describes what happened after the universe began expanding, but not necessarily why or how that expansion started. This is where the mystery deepens. One of the central questions is whether time itself began with the Big Bang. In standard cosmological models, time and space are both part of the universe. If the universe began at a specific moment, then time itself may have originated at that moment. This raises a difficult question. What does it mean to ask what happened before time began? In classical physics, asking what happened before the Big Bang may not be meaningful because the concept of before assumes the existence of time. If time itself emerged from the Big Bang, then there may be no earlier moment in the usual sense. Instead, the Big Bang would represent a boundary condition rather than an event in a pre-existing timeline. However, modern theoretical physics explores several possibilities that extend beyond this simple picture. One idea is that the Big Bang was not the absolute beginning, but rather a transition from a previous state of the universe. In this view, our universe may be part of a larger structure, possibly undergoing cycles of expansion and contraction or emerging from a previous phase. Cyclic universe models suggest that the universe could undergo repeated cycles of big bangs and big crunches. In such models, the universe expands for a long period, then eventually contracts under gravity, collapsing back into a dense state, which then triggers another expansion. However, current observations of dark energy suggest that the expansion of the universe is accelerating, making a future collapse less likely under standard assumptions. Another possibility is that the universe originated from a quantum fluctuation. In quantum mechanics, even empty space is not truly empty. It is filled with fluctuations that constantly create and annihilate particle pairs. Some theories suggest that the entire universe could have originated from such a fluctuation in a quantum vacuum, where a small region of space transitioned into a rapidly expanding state. There are also ideas involving inflation, a period of extremely rapid expansion that may have occurred very early in the universe's history. During inflation, space itself expanded exponentially in a fraction of a second. This process could explain the uniformity and structure of the universe we observe today. However, what triggered inflation and what existed before it remains uncertain. Some cosmological models propose that our universe is just one of many in a larger multiverse. In this view, what we call the Big Bang may be the result of a process occurring in a larger cosmic system that produces multiple universes, each with its own physical laws and constants. These universes may exist in separate regions of a higher dimensional space, or emerge from quantum processes on a grand scale. If the multiverse idea is correct, then the origin of our universe may not be a unique event, but one of many similar events occurring across a much larger reality. However, because other universes would likely be causally disconnected from ours, it may be impossible to directly observe them. Another important mystery is why the universe has the properties it does. The laws of physics, the values of fundamental constants, and the structure of matter all appear to be finely tuned in a way that allows complexity to exist. If these values were even slightly different, stars, galaxies, and life might not have formed. This raises the question of whether the universe's initial conditions were random, necessary, or the result of some deeper principle. Some scientists argue that there may be underlying physical laws that determine these constants. Others suggest that we observe this particular universe simply because only universes with such properties can support observers. As we look deeper into the early universe, we also encounter a fundamental limit known as the Planck epoch. This is the earliest period of time, up to about 10 to the power of minus 43 seconds after the Big Bang, where our current understanding of physics breaks down. At this scale, quantum effects of gravity become extremely important, and a full theory of quantum gravity would be required to describe the universe accurately. During the Planck epoch, space and time themselves may have behaved in ways that are completely different from anything we can currently understand. The structure of space-time may have been highly fluctuating, and the distinction between space, time, and energy may not have been well defined. Because we do not yet have a complete theory of quantum gravity, this earliest moment of the universe remains one of the greatest unknowns in physics. It represents the limit of what we can currently describe using known scientific laws. Despite these uncertainties, the Big Bang theory remains one of the most successful models in science. It explains the expansion of the universe, the existence of cosmic background radiation, the formation of light elements, and the large-scale structure of galaxies. Yet, it also points toward deeper questions that remain unanswered. The origin of the universe is not just about a moment in time. It is about the nature of existence itself. It challenges our understanding of causality, time, and reality. If time began with the universe, then the usual idea of cause and effect may not apply in the way we expect. In this sense, the origin of the universe may not have a simple answer. It may require new physics, new concepts of space and time, or even a completely different framework for understanding reality. This chapter reveals a universe whose beginning is both well described and deeply mysterious. We can trace its evolution back to its earliest moments, yet the ultimate origin remains hidden behind a boundary of unknown physics. The Big Bang is not just the start of everything we know, but also the edge of what we currently understand. The question of what came before the universe, or whether such a question even has meaning, remains open. It is one of the most profound mysteries in science, and perhaps one of the most fundamental questions that any intelligence can ask. Across the vastness of the universe, there is a silence that grows more puzzling the deeper we look. The cosmos is filled with billions of galaxies, each containing billions of stars, and around those stars countless planets. With so many opportunities for life to emerge, it seems natural to expect that intelligent civilizations should exist elsewhere. Yet despite decades of searching, we have found no confirmed evidence of extraterrestrial intelligence. This contradiction between expectation and observation is known as the Fermi Paradox. The question is simple but profound. If the universe is so large and so old, where is everyone? Why have we not seen clear signs of other civilizations, such as radio signals, megastructures, or interstellar visitors? The silence of the universe becomes even more striking when we consider the timescales involved. The Milky Way galaxy alone is over 13 billion years old, and Earth formed relatively late in cosmic history. If other civilizations arose even a few million years before us, they could potentially be far more advanced. To understand the paradox, we must first consider the conditions required for life. Life as we know it depends on several key factors, including the presence of liquid water, stable energy sources, and chemical elements such as carbon, hydrogen, oxygen, and nitrogen. These elements are not rare in the universe. They are produced in stars and distributed through supernova explosions. This means that the basic ingredients for life are widespread. Planets are also extremely common. Observations of exoplanets show that most stars have planetary systems. Many of these planets exist in what is called the habitable zone, where conditions might allow liquid water to exist. This suggests that potentially habitable environments are not rare, but abundant. Given this abundance of ingredients, it seems likely that life should arise in many places. On Earth, life appeared relatively early in the planet's history once conditions stabilized. This suggests that under the right conditions, life may not be extremely rare. However, the transition from simple life to complex intelligent life may be much more difficult. On Earth, life remained microbial for billions of years before complex multicellular organisms evolved. Intelligence capable of building technology emerged only in the very recent past of Earth's history. This suggests that while simple life might be common, intelligent life could be much rarer due to the long and complex evolutionary steps required. One possible explanation for the Fermi Paradox is that intelligent civilizations are extremely rare. Even if life is common, the conditions required for technological intelligence may be so specific that very few civilizations ever arise. This is sometimes called the rare Earth hypothesis, which suggests that Earth may have unusually favorable conditions for complex life. Another possibility is that civilizations tend to self-destruct before they become capable of interstellar communication or exploration. Technological advancement brings both power and risk. The development of nuclear weapons, environmental degradation, or other existential threats could limit the lifespan of civilizations. If most civilizations destroy themselves shortly after developing advanced technology, then the universe would appear quiet. There is also the possibility that civilizations choose not to communicate. Advanced societies may develop technologies or philosophies that prioritize isolation or non-interference. They may deliberately avoid broadcasting their presence or interacting with less advanced civilizations. In such a scenario, the silence of the universe would be intentional rather than accidental. Another explanation involves distance and time. The universe is incredibly large, and even at the speed of light, signals take thousands or millions of years to travel between stars. Civilizations may exist, but they could be too far away or too separated in time for their signals to overlap with ours. Civilizations may rise and fall without ever being aware of each other. The concept of cosmic time is important here. A civilization that existed millions of years ago in another part of the galaxy could have already disappeared by the time its signals reach us. Similarly, civilizations that arise in the future will not yet be detectable. We may simply be early or late in the timeline of intelligent life. Another idea is that advanced civilizations may evolve beyond physical forms that we can easily detect. They might transition into digital or artificial intelligence-based systems, or into forms of existence that do not rely on large-scale energy consumption. If this is the case, they may become nearly invisible to traditional astronomical methods. Some theories suggest that advanced civilizations might harness energy in ways that are difficult to detect from a distance. For example, a civilization could theoretically construct large-scale structures around stars to capture their energy. These structures, sometimes called Dyson spheres or Dyson swarms, would alter the way a star emits light. However, despite searches for such anomalies, no confirmed examples have been found. Another possibility is that interstellar travel is far more difficult than we imagine. Even if civilizations survive for long periods, the distances between stars are so vast that travel or communication may be impractical. The speed of light imposes a fundamental limit on how quickly information or matter can move. This could mean that even advanced civilizations remain confined to their own star systems. There is also the possibility that we are simply not looking in the right way. Our methods of searching for extraterrestrial intelligence are limited by our own technological assumptions. We primarily search for radio signals or other forms of electromagnetic communication, but other civilizations might use communication methods we do not yet understand or cannot detect. The silence of the universe could also be a reflection of timing. The age of the universe is finite, and intelligent life may only exist during certain windows of time. If civilizations tend to arise early or late in cosmic history, the chances of overlapping in time could be very small. Another intriguing idea is that life itself may be more fragile than we assume. While simple life might emerge easily, the progression to complex ecosystems and intelligent beings may require a long chain of stable conditions. Any disruption, such as asteroid impacts, climate instability, or stellar changes, could reset the evolutionary process. Despite these possibilities, the absence of evidence remains one of the most striking features of our observations. We have scanned the skies for decades, listening for signals and searching for anomalies, yet the universe appears quiet. This silence is not proof that we are alone, but it is a strong observational constraint on how common detectable civilizations might be. The Fermi Paradox does not have a single accepted solution. Instead, it is a collection of possible explanations that each address different aspects of the problem. It may be that several factors are combined, making intelligent civilizations rare, short-lived, distant, or difficult to detect. This mystery also raises deeper questions about our own future. If we are the only intelligent civilization in our region of the universe, or one of very few, then our responsibility becomes much greater. The future of intelligence in the cosmos may depend on how we navigate our own technological development and long-term survival. If we are not alone, but simply unable to detect others, then the universe may be filled with civilizations that are equally isolated. In that case, the silence is not absence, but separation. Each civilization may be living in its own cosmic island, unaware of others beyond its horizon. The Fermi Paradox ultimately reflects the tension between expectation and observation. The universe is vast, old, and rich in potential for life, yet it appears quiet. This contradiction remains one of the most important open questions in science. As we continue to explore the universe, search for exoplanets, and listen for signals from distant stars, we may eventually find clues that resolve this paradox. Or we may discover that the universe is more complex and silent than we ever imagined. This chapter reveals a cosmos that is both full of potential and strangely quiet. The ingredients for life are everywhere, yet the evidence for other minds remains absent. Whether this silence is temporary, natural, or profound remains one of the greatest mysteries in our understanding of the universe. Time is one of the most familiar aspects of human experience, yet it is also one of the most mysterious features of the universe. Every moment we live is defined by the passage of time, and everything we observe in the cosmos unfolds within its flow. Stars are born, evolve, and die over billions of years. Galaxies collide and merge across vast timescales. Even the smallest particles exist within a framework that depends on time. And yet, despite its central role in reality, the true nature of time remains deeply uncertain. One of the most striking features of time is that it appears to have a direction. We remember the past, but not the future. We see broken objects naturally fall apart, but never spontaneously reassemble. Ice melts into water, but water does not spontaneously turn back into ice under normal conditions. This one-way direction of time is known as the arrow of time, and it is one of the most important unsolved problems in physics. At the fundamental level, most physical laws do not distinguish between past and future. The equations that describe motion, gravity, electromagnetism, and even quantum mechanics generally work the same whether time moves forward or backward. This creates a paradox. If the laws of physics are time-symmetric, why does time appear to flow in only one direction in our experience? The most widely accepted explanation for the arrow of time is based on entropy. Entropy is a measure of disorder, or the number of possible microscopic arrangements that correspond to a macroscopic state. According to the second law of thermodynamics, entropy tends to increase over time in a closed system. This means that systems naturally evolve from states of low entropy to states of higher entropy. For example, a neatly arranged deck of cards represents a low entropy state. If the cards are shuffled, the number of possible arrangements increases dramatically, representing a higher entropy state. Once shuffled, it is extremely unlikely for the deck to spontaneously return to its original ordered state. This principle applies not only to everyday objects, but also to the universe as a whole. In the early universe, entropy was extremely low. The matter and energy were distributed in a highly uniform and ordered state. Over time, gravity caused matter to clump together, forming stars, galaxies, and larger structures. As these structures evolved, entropy increased. Stars burned their fuel, galaxies formed complex systems, and eventually black holes emerged, representing regions of extremely high entropy. The increase of entropy provides a natural explanation for the arrow of time. As entropy increases, processes become irreversible in practice, even if they are reversible in theory. This creates the experience of time flowing in one direction. We remember lower entropy states in the past and observe higher entropy states in the present and future. However, this explanation raises a deeper question. If entropy always increases, why was the early universe in such a low entropy state to begin with? This is one of the most fundamental mysteries in cosmology. The initial conditions of the universe appear to be highly special, allowing for the existence of an arrow of time. Another aspect of time is its connection to space. According to Einstein's theory of relativity, space and time are not separate entities, but are combined into a single structure known as space-time. Events in the universe are described by their position in both space and time. This means that time can behave differently depending on the observer. One of the most important consequences of relativity is time dilation. Time does not pass at the same rate for all observers. For objects moving at high speeds or in strong gravitational fields, time passes more slowly compared to observers in weaker gravitational fields or lower speeds. This has been confirmed through many experiments, including observations of particles in accelerators and clocks placed at different altitudes on Earth. Near massive objects like black holes, time dilation becomes extremely strong. An object approaching the event horizon of a black hole appears to slow down relative to a distant observer. From the perspective of the falling object, however, time continues normally. This difference highlights the relative nature of time in extreme gravitational conditions. In the expanding universe, time is also affected on cosmic scales. As space expands, distant galaxies appear to move away from us, and their light is stretched to longer wavelengths. This phenomenon, known as redshift, is directly related to the expansion of space over time. It shows that time and the evolution of the universe are deeply connected. Another important question is whether time had a beginning. In standard cosmological models, time began with the Big Bang. Before this event, there was no classical notion of time or space as we understand them. This raises the question of what it means for time itself to begin. If time began at the Big Bang, then asking what happened before, it may not be meaningful in the usual sense. The concept of before assumes the existence of time, so if time itself started at that moment, then there may be no earlier state in the traditional framework. However, this does not necessarily mean that the Big Bang was the absolute beginning of everything. Some theories suggest that time may be emergent rather than fundamental. In this view, time arises from more basic physical processes rather than existing independently. If this is true, then what we perceive as time could be a large-scale effect of underlying quantum or geometric structures. Other theories propose that time may extend beyond the Big Bang in ways that are not yet fully understood. In cyclic models, time may extend through multiple phases of expansion and contraction. In multiverse models, different regions of space-time may have different time origins. In quantum cosmology, time may emerge from a timeless quantum state. The nature of time also becomes even more mysterious at the smallest scales. In quantum mechanics, time is treated differently from space. It is often considered an external parameter rather than an operator like position or momentum. This creates a tension between quantum mechanics and general relativity, where time is dynamic and influenced by gravity. One of the major goals of modern physics is to develop a theory of quantum gravity that unifies these two descriptions. Such a theory would likely change our understanding of time at the most fundamental level. It could reveal whether time is continuous or discrete, whether it is fundamental or emergent, and whether it behaves the same at all scales. Another intriguing aspect of time is its relation to causality. Causality is the idea that cause precedes effect. This principle is deeply embedded in our understanding of the universe. However, in certain solutions of general relativity, exotic structures like closed time-like curves could theoretically allow for paths in space-time that loop back in time. These ideas raise the possibility of time travel, although their physical reality remains highly speculative. Even in quantum mechanics, time behaves in ways that challenge classical intuition. Particles do not have definite histories in the classical sense, but are described by probabilities and wave functions. This means that at fundamental levels, the concept of a single definite timeline becomes less clear. As we consider the universe on the largest scales, time is closely tied to its ultimate fate. In an ever-expanding universe dominated by dark energy, time continues indefinitely, but physical processes gradually slow as entropy increases. Eventually, the universe may reach a state where no significant change occurs, even though time itself continues to pass. This leads to a philosophical question. If nothing changes, does time still have meaning? In a universe where all processes have ceased, time may exist mathematically, but have no observable consequences. This highlights the deep connection between time and physical change. The arrow of time, the expansion of the universe, and the evolution of complexity are all deeply linked. From the earliest moments after the Big Bang to the far future of cosmic expansion, time defines the structure and behavior of everything in the universe. Yet, its true nature remains one of the most profound mysteries in science. This chapter reveals time not as a simple flowing river, but as a complex and deeply interconnected feature of reality. It is shaped by entropy, influenced by gravity, tied to the structure of space-time, and possibly emergent from deeper physical laws. And yet, despite its central role in everything we observe, time remains one of the least understood aspects of the universe. Understanding time may ultimately require a revolution in physics, one that changes not only how we describe the universe, but how we understand existence itself. One of the most intriguing ideas in modern cosmology is the possibility that our universe is not the only one. Instead, it may be just one of many universes existing within a much larger framework. This concept is known as the multiverse, and while it remains highly theoretical, It arises naturally in several areas of physics, including quantum mechanics, cosmology, and theories of fundamental forces. The idea of multiple universes challenges one of the most basic assumptions in science, that everything that exists is contained within a single, unified cosmos. Instead, the multiverse suggests that reality may be far more extensive, with countless universes existing beyond our observational reach, each potentially governed by different physical laws, constants, and structures. One of the simplest motivations for the multiverse comes from cosmic inflation. Inflation theory proposes that in the earliest fraction of a second after the Big Bang, the universe underwent an extremely rapid expansion. This expansion smoothed out the observable universe and explains many of its large-scale properties, such as its uniformity and flatness. However, some versions of inflation theory suggest that inflation may not have stopped everywhere at once. Instead, different regions of space could have stopped inflating at different times, while other regions continue inflating indefinitely. This leads to a scenario known as eternal inflation, where inflation is ongoing in some parts of the larger space-time while producing separate bubble universes in others. In this picture, our universe would be just one bubble in an ever-expanding, inflating background. Each bubble universe could have its own distinct properties, depending on how inflation ended within it. The laws of physics, particle types, and even the number of dimensions could vary from one bubble to another. Another source of multiverse ideas comes from quantum mechanics. According to one interpretation of quantum theory, known as the many worlds interpretation, every quantum event results in a branching of reality. Instead of a single outcome occurring, all possible outcomes happen, each in its own separate branch of the universe. In this view, the universe constantly splits into multiple parallel versions, each representing a different possible outcome of quantum events. Every decision, every particle interaction, and every random event leads to a branching of reality. Although these branches cannot interact or communicate, they all exist simultaneously within a larger quantum framework. If this interpretation is correct, then the multiverse is not only vast in space, but also in quantum possibility. Every version of reality that could have happened, no matter how unlikely, exists in some branch of the universal wave function. This leads to an almost unimaginable number of parallel histories. Another form of multiverse arises from string theory, a theoretical framework that attempts to unify all fundamental forces and particles. String theory suggests that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. The properties of these strings depend on how extra spatial dimensions are compactified or shaped. In string theory, there are many possible ways for these extra dimensions to be configured. Each configuration could lead to a different set of physical laws. This results in a vast landscape of possible universes, each with its own version of physics. Some estimates suggest that the number of possible configurations could be extremely large, potentially on the order of 10 to the power of hundreds or even more. This idea is often referred to as the string landscape. In this framework, our universe is just one possible solution among an enormous number of mathematically consistent universes. The specific properties of our universe, such as the strength of forces and the masses of particles, may simply be one realization within this broader landscape. The multiverse concept also appears in cosmological discussions of fine-tuning. The physical constants of our universe appear to be finely balanced in a way that allows complex structures and life to exist. If these constants were slightly different, stars might not form, chemistry might not function, or stable matter might not exist. The multiverse provides a possible explanation for this fine-tuning. If there are many universes with different physical constants, then it is not surprising that at least one of them, ours, has conditions suitable for life. We observe this universe because only in such a universe can observers exist. This idea is known as the anthropic principle. However, the multiverse raises deep philosophical and scientific challenges. One of the biggest problems is that other universes, if they exist, may be fundamentally unobservable. If they are separated from us by cosmic inflation, quantum branching, or higher dimensional structures, then no information from those universes can reach us. This makes direct testing extremely difficult. Science relies on observation and experiment, so a theory that cannot be tested poses a challenge to traditional scientific methodology. Some physicists argue that the multiverse is a natural consequence of well-established theories and should be accepted if those theories are correct. Others argue that without direct evidence, the multiverse remains speculative. Despite this, the multiverse idea continues to gain attention because it provides potential explanations for several otherwise puzzling features of the universe. It offers a way to understand why physical constants appear finely tuned, why quantum mechanics behaves probabilistically, and why inflation seems to produce a large and uniform cosmos. If the multiverse exists, then reality is far larger than what we can observe. Our universe would be just one region within a much greater structure, possibly infinite in extent. Each universe could have its own history, its own laws of physics, and its own possibilities for complexity and life. In some multiverse models, universes may even interact indirectly. For example, in eternal inflation, bubble universes might occasionally collide, potentially leaving imprints in the cosmic microwave background radiation. Scientists have searched for such signatures, but no definitive evidence has been found so far. Another important question is whether the multiverse is truly infinite or simply extremely large. If space extends infinitely, then even without separate universes, there could be infinitely many regions similar to ours. In such a case, every possible configuration of matter might repeat somewhere in the universe, leading to a form of cosmic repetition. In an infinite universe, there could be regions identical to our own, containing copies of Earth, the solar system, and even versions of ourselves. These identical regions would be so far away that they could never be observed, but they would exist as a consequence of infinite space and finite possible arrangements of matter. Whether through quantum branching, cosmic inflation, string theory landscapes, or infinite space, the multiverse challenges our understanding of reality at the most fundamental level. It suggests that what we perceive as the universe may be only a small part of a much larger structure. However, without direct observational evidence, the multiverse remains one of the most debated ideas in physics. It sits at the boundary between science and philosophy, where mathematical consistency meets empirical uncertainty. Its existence cannot yet be confirmed, but its implications are profound. If the multiverse is real, then the concept of uniqueness changes dramatically. Our universe would not be the only one, and perhaps not even special in a physical sense. Instead, it would be one realization among countless possibilities, each unfolding in its own domain. This chapter reveals a cosmos that may extend far beyond what we can ever observe. Whether through inflation, quantum mechanics, or fundamental theory, the idea of multiple universes suggests that reality itself may be far larger, more diverse, and more complex than we ever imagine. The universe we observe is built on three familiar spatial dimensions and one dimension of time, forming what we call space-time. This framework has successfully described everything from the motion of planets to the expansion of the cosmos. Yet, despite its success, modern theoretical physics suggests that space-time may not be as simple as it appears. Beneath the surface of our everyday reality, there may exist additional, hidden dimensions that we cannot directly perceive. The idea of extra dimensions did not begin as science fiction, but as a mathematical attempt to unify the forces of nature. In the early 20th century, physicists tried to combine gravity and electromagnetism into a single framework. One of the earliest attempts came from the Kaluza-Klein theory, which proposed that if a fifth dimension were added to space-time, the equations of general relativity could naturally include electromagnetism as well. According to this idea, the extra dimension is not visible because it is compactified, meaning it is curled up into an extremely small size, far smaller than anything we can currently detect. Imagine a long, thin hose from a distance. It appears as a one-dimensional line, but up close you can see that it has a circular cross-section. Similarly, space could have additional dimensions that are simply too small to observe at macroscopic scales. Modern theories, such as string theory, take this idea even further. In string theory, the fundamental building blocks of nature are not point-like particles, but tiny, vibrating strings. For the mathematics of string theory to be consistent, the universe requires more than 4 dimensions. In many versions of the theory, space-time must have 10 or even 11 dimensions. These extra dimensions are not extended like the 3 we experience. Instead, they are compactified into complex shapes at extremely small scales. The specific shape of these extra dimensions determines the properties of particles and forces in the observable universe. Different shapes can lead to different physical laws, meaning that the structure of hidden dimensions could define the very nature of reality. This idea introduces a profound possibility. The laws of physics that we observe may not be fundamental in a universal sense. Instead, they could be the result of how extra dimensions are configured in our region of space-time. Other regions of a larger multiverse could have different configurations, leading to entirely different physical laws. One of the key motivations for extra dimensions is the unification of forces. In physics, there are 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While electromagnetism and the nuclear forces have been successfully described within quantum field theory, gravity remains difficult to unify with quantum mechanics. Extra-dimensional theories offer a possible solution. In these frameworks, gravity may propagate through higher dimensions, while other forces are confined to a lower dimensional surface, often called a brane. This idea leads to the concept of brane cosmology, where our observable universe is a three-dimensional surface embedded in a higher dimensional space. In such models, what we perceive as reality could be like a membrane floating within a larger dimensional structure. Other branes could exist parallel to ours, separated by extra dimensions that we cannot access directly. These parallel branes could have their own universes, possibly with different physical laws and histories. Although these ideas are mathematically consistent in some frameworks, they are extremely difficult to test experimentally. The energies required to probe extra dimensions are far beyond the reach of current particle accelerators. However, scientists are searching for indirect evidence, such as deviations in gravitational behavior at very small scales or unusual particle interactions. One possible sign of extra dimensions would be a deviation from the inverse square law of gravity at short distances. If gravity can spread into additional dimensions, its strength could change in ways that differ from predictions based on three-dimensional space. So far, experiments have not found any clear evidence of such deviations, but the possibility remains open. Another potential signature comes from high-energy particle collisions. If extra dimensions exist, particles could gain access to them under extreme energy conditions. This could result in missing energy signatures or the production of exotic particles that escape into higher dimensions. Experiments at particle colliders continue to search for such effects. The existence of hidden dimensions would fundamentally change our understanding of space. What we perceive as empty space might actually be a complex structure with hidden geometry. The shape and size of these dimensions could influence everything from the mass of particles to the strength of forces. In some theories, gravity is especially important in connecting visible and hidden dimensions. Unlike other forces, gravity might be able to spread through all dimensions, which could explain why it appears so much weaker than the other fundamental forces. This is sometimes called the hierarchy problem in physics. If gravity is diluted across extra dimensions, then its apparent weakness in our three-dimensional space would be an illusion caused by its spread into a larger structure. This idea provides a possible explanation for why gravity is so much weaker than electromagnetism, despite both being fundamental forces. Extra dimensions also raise the possibility of new types of particles or fields that exist only in higher dimensional space. These could interact with our universe in subtle ways, possibly contributing to phenomena such as dark matter or dark energy. Some theories even suggest that dark matter could be a manifestation of particles moving through extra dimensions. Another fascinating implication is the possibility of shortcuts through space-time. If extra dimensions exist, then what appears to be a long distance in three-dimensional space might be much shorter when viewed through higher dimensional geometry. This has led to speculative ideas about wormholes, which are hypothetical structures that connect distant regions of space-time through higher dimensions. Wormholes, if they exist, could theoretically allow travel between distant parts of the universe or even between different universes. However, there is currently no experimental evidence that such structures exist or can remain stable. Most models suggest that they would require exotic forms of matter or energy that have not been observed. The idea of hidden dimensions also connects deeply with the concept of quantum gravity. At extremely small scales, near the Planck length, space-time itself may become quantized or discrete. In such conditions, the smooth geometry of space-time may break down, revealing a more fundamental structure that includes additional dimensions or complex topologies. Understanding these hidden dimensions could be key to unifying general relativity and quantum mechanics. While general relativity describes gravity as curvature of space-time, quantum mechanics describes particles as probabilistic wave functions. A theory that includes extra dimensions might provide the missing link between these two frameworks. Despite its elegance, the idea of extra dimensions remains unproven. It exists at the edge of theoretical physics, supported by mathematical consistency, but not yet confirmed by observation. This makes it one of the most exciting and speculative areas of modern science. If extra dimensions are real, then the universe is far more complex than it appears. Our familiar three-dimensional world would be just a slice of a much richer structure. Reality itself would extend beyond our sensory experience, hidden in directions we cannot directly perceive. This raises a profound question about the nature of existence. If there are dimensions beyond our perception, then what we call reality is only a limited projection of a deeper structure. Our understanding of space, motion, and even causality might be incomplete. In the far future, if humanity or any advanced intelligence develops the ability to probe these hidden dimensions, it could revolutionize physics. It might allow access to new forms of energy, new methods of travel, or entirely new frameworks for understanding the universe. For now, extra dimensions remain a theoretical possibility. They are supported by mathematical elegance and appear naturally in attempts to unify the forces of nature, but they remain hidden from direct observation. Like many mysteries in cosmology, they challenge the boundaries between what is known and what is possible. This chapter reveals a universe that may be far richer than it appears. Beneath the surface of visible space, there could be hidden dimensions shaping the laws of physics and the structure of reality itself. Whether these dimensions exist or remain mathematical abstractions, they represent one of the deepest and most intriguing questions in modern science. At the edge of all scientific understanding lies a collection of questions that do not belong to any single field of physics, yet touch every part of it. These are not ordinary unsolved problems, but fundamental gaps in our knowledge that define the limits of what we currently know about reality itself. They are the questions that remain even after we have built models for the Big Bang, mapped galaxies across the universe, detected black holes, and described the behavior of particles with extraordinary precision. This final chapter brings together those deepest uncertainties, the ultimate unknowns of the cosmos. One of the most profound of these mysteries is the nature of reality itself. We describe the universe using mathematical laws, equations, and models, Yet we do not fully understand why these laws exist in the form they do. The universe behaves in a consistent and predictable way on large scales, but the reason it follows these specific rules rather than others remains unknown. Why does gravity have the strength it does? Why do particles have the masses they do? And why do the fundamental forces take the forms we observe? These are not questions of detail, but questions about the foundation of existence. Closely related to this is the question of why there is something rather than nothing. In physics, even empty space is not truly empty. It contains fields, fluctuations, and energy. But why does this structure exist at all? Could there have been a state with no space, no time, no energy, and no physical laws? If so, why did the universe not remain in such a state? Or why did it transition into the one we observe? This question lies at the boundary between physics and philosophy, yet it is unavoidable in any attempt to understand the cosmos. Another major unknown concerns the unification of physics. Today, we have two extremely successful frameworks: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes particles and forces at the smallest scales. Both theories have been tested with extraordinary accuracy, yet they are fundamentally incompatible in certain extreme conditions, such as inside black holes or at the very beginning of the universe. A complete theory of quantum gravity would be needed to unify them, but such a theory has not yet been confirmed. This missing theory is not just a technical detail. It may hold the key to understanding the true nature of space-time, the origin of the universe, and the behavior of black holes. Without it, our picture of reality remains incomplete at its most fundamental level. We can describe the universe with remarkable precision across many scales, but there is a gap at the deepest foundation where our current understanding breaks down. Another unresolved mystery is the nature of time at the most fundamental level. We experience time as continuous and flowing, but it is not clear whether time is truly fundamental or emergent from deeper physical processes. Some theories suggest that time may arise from quantum entanglement or thermodynamic relationships rather than existing as a basic dimension. If this is true, then what we perceive as the flow of time may be a large-scale effect of more fundamental structures. Connected to this is the question of the arrow of time. The laws of physics do not strongly prefer a direction of time, yet the universe clearly evolves in one direction, from lower entropy to higher entropy. Why the early universe began in such a low entropy state remains one of the most important unsolved problems in cosmology. Without this initial condition, the directionality of time as we experience it would not exist. The origin of the universe itself remains deeply mysterious. While the Big Bang theory describes the evolution of the universe from an early hot, dense state, it does not fully explain why that state existed in the first place. Whether time began at that moment or whether something preceded it is still unknown. Some models suggest a multiverse, others suggest cyclic universes, and others propose quantum origins, but none have been confirmed. Dark matter and dark energy remain two of the most significant missing pieces in our understanding of the universe. Together, they make up the vast majority of the universe's total content, yet neither has been directly observed in a laboratory. We only know them through their effects on galaxies, expansion, and cosmic structure. Their true nature could reveal entirely new forms of physics beyond the standard model. Dark matter shapes the structure of galaxies, while dark energy drives the expansion of the universe. Yet both remain invisible and unexplained. If we were to discover their true nature, it could completely transform our understanding of cosmic evolution and fundamental physics. The question of whether we are alone in the universe also remains unanswered. The Fermi Paradox highlights the contradiction between the high probability of life elsewhere and the lack of any confirmed evidence of extraterrestrial intelligence. This silence could mean that intelligent life is extremely rare, or that civilizations are separated by vast distances in space or time, or that advanced civilizations do not communicate in ways we can detect. Another possibility is that life is common, but technological civilizations are short-lived. Self-destruction, environmental collapse, or natural cosmic hazards could limit the lifespan of intelligent species. In this case, civilizations may arise and disappear without ever making contact with one another. The nature of consciousness itself is another deep mystery that intersects with cosmology. We do not fully understand how subjective experience arises from physical processes in the brain. While neuroscience has made great progress in understanding brain activity, the reason why certain physical processes produce conscious awareness remains unknown. If consciousness is tied to fundamental physics in ways we do not yet understand, it could change how we view life in the universe. There are also questions about the ultimate fate of the universe. Current evidence suggests that the universe will continue expanding indefinitely, driven by dark energy, eventually leading to a state of extreme isolation and low energy density. In this scenario, stars will burn out, black holes will evaporate, and matter may decay, leaving behind a cold and nearly empty universe. However, this prediction depends on our current understanding of dark energy, which is still incomplete. If dark energy changes over time, the future of the universe could be very different. It could slow, reverse, or even increase in strength, leading to radically different outcomes, such as a big freeze, big crunch, or big rip. Each possibility reflects a different unknown in the underlying physics of cosmic expansion. There are also mysteries related to the fine-tuning of physical constants. The universe appears to have values for fundamental quantities that allow for the existence of complex structures and life. If these values were slightly different, the universe might be radically different or incapable of supporting complexity. Whether this fine-tuning is a result of deeper physical laws, chance, or a multiverse selection effect remains unknown. On the smallest scales, quantum mechanics continues to raise questions about the nature of reality. Particles do not have definite properties until they are measured, and their behavior is described by probabilities rather than certainties. What this means for the underlying structure of reality is still not fully understood. The measurement problem in quantum mechanics remains one of the most debated topics in physics. Even the structure of space itself may not be fundamental. Some theories suggest that space-time could emerge from more basic elements, such as quantum information or entanglement networks. If this is true, then space and time as we experience them are not the deepest level of reality, but emergent properties of something more fundamental. All of these mysteries point toward a central truth. Our understanding of the universe, while extremely powerful, is still incomplete. We can describe the evolution of galaxies, the behavior of black holes, the expansion of space, and the properties of particles with remarkable accuracy. Yet, at the deepest level, we still do not know why the universe exists in the form it does. The unknown is not confined to one area of physics. It appears at every scale, from the smallest particles to the largest structures, from the beginning of time to its possible end, from the nature of space to the nature of consciousness itself. The universe is not only what we understand, but also what we do not yet understand. This final chapter brings together all of these open questions, not as isolated problems, but as parts of a larger picture. They are connected in ways we are only beginning to understand. Solving one mystery may unlock others, and a deeper theory of reality may eventually unify them into a single framework. Until then, the universe remains both known and unknown, familiar and mysterious, understandable and beyond reach. It is a place where every answer leads to new questions, and every discovery reveals deeper layers of complexity. The ultimate unknown of the cosmos is not just one question, but the recognition that reality itself is still incomplete in our understanding, and perhaps that is the most profound mystery of all.